Today we're going to go over Big Idea 7, Standard 5, which is potential energy diagrams. So we talked a little bit about potential energy at the beginning of this unit. Potential energy is stored energy, and potential energy is going to be stored within chemical bonds. So if we look at what happens to our potential energy as a reaction progresses, potential energy is going to increase when bonds are broken. In order to progress from reactants to products, we need to break those bonds between the reactants. When we break those bonds, we release that potential energy. When we form new bonds, potential energy is going to decrease. So we're always going to have a shape similar to this diagram here, where we see the potential energy increases as we break the bonds of the reactants, and then potential energy will decrease when we form new products. So you need to be able to label potential energy diagrams, and there's a few points that you need to know. The activated complex is always going to be the tallest portion of your curve. The activated complex is kind of like a transition state between reactants and products. This is going to be high energy, it's going to be unstable. This is going to be kind of that state where we're transitioning from our reactants to our products. Next, the reactants are always going to be on the left side. Just like in a chemical reaction, reactants are on the left, products are on the right. So right here will tell me the potential energy of the reactants, and down here would be the potential energy of the products. Activation energy is going to range from the reactants up to the activated complex. So my activation energy is going to be right in here. Activation energy is going to be EA for short. Activation energy is the minimum energy required for a reaction to occur, and it is always going to be a positive number. So in a little bit, we're going to do some calculations, and you're going to have to calculate activated complex. It should always be positive. Lastly, our change in enthalpy, delta H. This just tells me the total energy change for the reaction. And delta H is going to be the difference between the products and reactants. So here is the potential energy of my products. Here is the potential energy of my reactants. So this range is going to be my delta H value. Delta H can tell us a few things about the reaction, and it's going to be the same as Q, so that should be easy to remember. If Q was positive, we would have an endothermic reaction. If delta H is positive, it is endothermic. In an endothermic reaction, energy gets absorbed. If Q was negative, we said it was exothermic. So if delta H is negative, the reaction is exothermic. If it's exothermic, energy is exiting or energy gets released. Alright, so let's look at two examples and we'll do some practice problems. So you should be able to label the reactants. Reactants are always on the left. Products are always on the right. Alright, activation energy is going to be the difference between the activated complex, which is the tallest portion of the graph, and all the way down to the reactants. My delta H value is the difference between my products and reactants. Next, we should be able to determine activation energy. Well, the activated complex is at 80 kilojoules. My reactants are at 30 kilojoules. So my activation energy is 50 kilojoules. That is the minimum energy required for this reaction to occur. Next, calculate delta H. Well, delta H is going to be equal to products minus reactants. Energy of the products is 50 kilojoules. Energy of the reactants is 30 kilojoules. So delta H would be 20 kilojoules. Really important that you always do products minus reactants, because based on the sign of delta H, you should be able to determine what type of reaction this is. So delta H is positive, meaning this reaction is endothermic. If it's endothermic, energy would be absorbed. The other way we can tell that this is endothermic without doing any calculations is just by looking at the shape of the curve. We start with less energy than we end with. So this reaction gained energy. If it's gaining energy, energy is being absorbed, it's going to be endothermic. Alright, pause the video, try this one on your own. When you're ready, unpause, come back and check your answers. So first thing we're going to do is label. So again, the reactants are always on the left. Products are always on the right. Activation energy is going to be the range from the activated complex, which is that tallest portion of the graph, and the reactants. So this would be my activation energy. Delta H is going to be the difference between the products and the reactants. Determine delta H. Whenever we're calculating our change in enthalpy, again, we always want to do products minus reactants. My products are at 20 kilojoules of energy. The reactants are at 70 kilojoules. So delta H would be negative 50. Since delta H is negative, this reaction would be exothermic. The other way we can tell it's exothermic is because it is losing energy. The reactants start with more energy. As the reaction progresses, we lose energy. So since we lose energy as the reaction progresses, energy is exiting the system. If energy is exiting the system, it's an exothermic reaction.